Hello, welcome back to the today class. Today I'd like to continue on our prior discussions on configuration space. So today, these are the today class objectives. I will talk about the obstacles, what are the passes of metrics in the context of the DC space. Also, the details about these concepts are actually already mentioned, already discussed in the chapter 3 of my draft. So last time we talked about the DOF, degrees of freedom of the C space. Also we talked about many other these constraints like holonomic, non-holonomic, also the dynamic constraint. So you may remember that before we talked about the free space, also this configuration space obstacle. In short, this C obstacle space. So let me recall you how we can compute this obstacle space. Basically, here we have this kind of obstacle shown in this kind of polygonal shape, and then we have this ball. This ball, the circle-shaped robot, and then the center of the circle is our reference point. So if we want to compute the obstacle space, we can roll this circle under along this boundary of the obstacle, right? Then basically the trajectory of the center of the circle give us the boundary of boundary of this C obstacle. So then if we visualize it, okay, here we do that, and then if we visualize it, then basically this trajectory of this center of the circle mapping to this boundary of boundary of this C obstacle space in the C space. So in other words, if we put the center of the this robot in the C space, basically if we know this information, we can very easily know that in this region we don't have any collision. Here we have actual collision, right? So early on in the field of robotics, actually a lot of people wanted to compute this C obstacle space, since we know that we can actually address a lot of problems of the motion planning. So now let's extend our discussion into this kind of triangular shaped robot. So here this triangular shaped robot, and then also this is a reference point. So in other words, actually the xy of this the robot is the parameter of our this C space. And then in this case also we can rotate it. Here we set this orientation of robot, we set that to be the 0. And then this is our workspace, and this is the red rectangle is the obstacle. And if we put this robot here at that point, we know that at that case we have collision, right? And then to compute this C obstacle space in the C space, we can also do the same similar thing. In other words, we slide this point robot while while keeping the touch with this obstacle. Then if we do that, if we visualize the trajectory of our reference point, we can see that these are actually that trajectory, and you can see that that's the boundary of the C obstacle space in the C space. So here you can see that if you put the robot here, we have contact there. If we slide through, then at that case, this is actually this corner of the obstacle. Then we actually passing through this triangle robot in this way. So as you can see, basically this reference point moving from here to there. That's why actually we have this kind of shapes. Okay, so basically this is actually our 2D visualization of the C space. Assuming that the orientation of the triangle robot is set to be 0. But we can also change it, right? In other words, our C space actually not 2D, actually 3D. But for simplicity, we set our orientation in this case. This value, the 30 degree, and then we do the same thing. And then somehow this trajectory actually missing. As you can see, but the trajectory of this reference point looks like this. Somehow I made this one. Somehow this line is gone. Anyway, if we visualize it, this reference point and then this C obstacle space in the C space, you can actually have this one. In other words, as we changing the orientation, this actually the 2D visualization at a particular theta value, also another 2D visualization with another this heading, right? So basically, you can see that as we change the orientation, this 2D space, 2D C obstacle space are changing, right? So if we put them together in the 3D space, the 3D C space x and y of the reference point, also this orientation, then basically you can see that this the C space, this is actually C obstacle space at the theta 0. This also C obstacle space at the theta to be 30 degree. Then in between, obviously the shape will be changing, right? So the main message that I give you is that the C obstacle space actually becomes very complicated in this original DC space. So in other words, this intuitively we can see that computing the C obstacle space may be very difficult. So now I'll talk about this C obstacle construction method. Input here we assume that input is the polygonal moving object. Here sometimes I use the robot, or sometimes I use this moving object. The polygonal moving object, nothing but robot, translating into the workspace. Just simple cases. Also we assume that obstacle also given with the polygonal shapes. And then the output is that we want to compute configuration space obstacle. In other words, this C obstacle space represented as these polygons. These are our input and output. Then how we can do that? So you will see that along that line, this Minkowski sum is a very useful operator. Some of you may heard about this Minkowski sum. So Minkowski sum between two sets, let's say P and Q. So basically, in this case, the set of P may contain the vertices of your polygon. The Minkowski sum between two sets P and Q, denoted by this one, P and Q, the Minkowski sum, is defined by this simple operator. Basically, we get the two vector or the two vertices from the P and Q, and then we're just adding, and then that's the actual Minkowski sum. Also, this one example. Here actually I had this kind of triangle, and also you can see that this P set, the set of P, they contain this vertex, and then we interpret them as a polygon, and then this another triangle represented by the Q. Then if we're adding them, basically at that point we're adding all these actually the vertex. Then we can actually have this kind of shape, right? You can see that we have this kind of shape, and then at that point also we're adding this one. Then we can have this shape, right? We can have this shape. Also, along this one, also we need to actually every point on this edge we also do the same thing. Then if we keep doing that, you can see that you can have the Minkowski sum between these two triangles can have this kind of polygon. That's the Minkowski sum. And also, in a similar way, we can define the Minkowski difference between two sets. And basically, Minkowski difference between P and Q is simply we get the P and Q from the P set Q set, and we just taking the vector vector minus operations. In other words, we can also transform this Minkowski difference to this Minkowski sum by taking the minus Q. That's the main concept of Minkowski sum and difference. And also before we move on, how we can use this Minkowski sum for computing C obstacle space. As you can see, Minkowski sum in the case of two convex polygon P and Q, and each one of these polygons has n vertices. Then if we do the Minkowski sum, it gives us another convex polygon that has the n plus n vertices. So actually, I'm showing this same example. Here actually we had these three different vertices. They are actually also these convex shapes. Then you can see that I'm just giving you one example. Here you can see that is another convex polygon with these 6 different vertices. That's one of the actual observation. Also, the one can prove this one. But actually proving this equation, proving this one is not not within our main topic. So I will just skip that one. So then, basically now, let me talk about what are the relations between the C obstacle space, also this Minkowski sum. Suppose that here, this P is actually the obstacle again, the rectangular shape, and in the workspace, and M is the moving robot, and the robot actually looks like this, the triangle shape again, and this is our reference point. I would say that origin. Then, as I mentioned before, basically these blue lines actually showing the boundary of our C obstacle, right? So if we put this robot, the reference point at that case, at this point, then you can see that the robot actually touching here. We have collision between this robot and the robot M, also this polygon P. Then we know that actually this point, right? The point where we have collision, right? But at that case, actually, the corresponding point in the C obstacle space is like this, right? Actually, when you put our reference point or point here, we will have the contact, right? Then here, basically, we have the collision there, right? While we have point in the C obstacle space there, right? For that point, one can see that basically we fetching one vertex from the obstacle here. Let's say this vector, assuming that this was also the origin vector. Basically this one vector, right? And then also if we actually pin out that particular point from in the perspective robot, also we get this vector, right? From this reference point of robot. So actually you can see that we have two vectors here. This vector from the obstacle, also another vector from the robot, right? Then how can you compute this? How can you compute this vector? They're referencing they're indicating to the reference point of the robot where we have contact in the C space. Then as you can see, this vector is summation between the basic difference between this P vector and also this minus M vector. So that's why you can see that the C obstacle space. In this case, mapping to the Minkowski difference between this obstacle and also this robot M. That's why actually one can prove that the boundary of C obstacle space can be computed by this Minkowski difference between P and M. So I'm not going to talk about how we can actually implement this Minkowski sum for computing C obstacle. But one intuition is that here actually if we one obstacle, one robot, if we do the Minkowski sum, basically here actually I said this C obstacle space is the Minkowski difference between P and M, but this also corresponding to the Minkowski sum between P and minus M. So actually I will just use that. We can just using the Minkowski sum for computing the C obstacle space. Then here, if we do the Minkowski sum between these two convex shapes, we can have this one, right? We can have this kind of polygon shape. But to do that, for each edge, we actually this vector actually normal. We get we visualize this normal into the here. Also, we visualize normal of this obstacle into there. Then for each normal, this normal, actually the one edge of the Minkowski sum mapping to there, and for normal we also this kind of the property. Based on that, we can actually there are some of algorithms that we can compute this kind of C obstacle space. But I'm not going to talk about the low level details here. But anyway, so at that cases and at the simple 2D cases, the running time of the Minkowski sum turn out to be the big O of n plus m. N is the vertices of vertices on one object. M is the vertices of another object. But here we assume that it's convex one, right? But in a lot of cases, the obstacle of the robot can be the non-convex. In that case, we have to decompose these kinds of convex, non-convex object into the convex polygons, like the triangles and some other one. Then also we need to compute the Minkowski sum between them. Also we need to take these geometric operations of union. Then it turns out that at that cases, actually complexity of the Minkowski sum turn out to be just assume that n is the same to the m. Then in this case, for non-convex shape, in the 2D case, the complexity of the Minkowski sum turn out to the big O of n to the power 4. In 3D case, it turned out to be the non-convex cases. The time complexity is the big O of the n to the power 6, which is actually very high and we cannot use it, right? But this is actually some of the illustration. This is actually this is one object. So another object is another object. If we do the actual Minkowski sum, as you can see, the Minkowski sum of these two objects looks very complicated here, right? So basically, you can see that why we get this time complexity of the n to the power 4 coming from here. There are a lot of these very detailed actually geometry and new features. Because of that, actually the data it requires a lot of complexity. For 3D cases, this one object that has about 400 triangle, another object has 1000 triangle. If we do the Minkowski sum, then this is actually the end result that consists of the 66,000 triangles, 66,000 of these primitives, which is a lot, right? So back then there has been a lot of research how we can do the efficiency compute this Minkowski sum, since actually this Minkowski sum used a lot for different geometry operations, including even the computing the C-optical space, which is very important for the motion planning. But main message is that computing the free or optical space in an accurate way is actually very expensive and non-trivial problem actually. So there, in other words, it's basically toward achieving this goal is very difficult problem. As a result, a lot of recent technique actually moves to some of the approximate technique or some other approach, like using some of the desampling based techniques. Also, using some of this probabilistic approach to avoid this kind of exact way. So, but nonetheless, actually, some of the recent techniques utilizing some of the geometry concepts that we talked about here. So, in some of the recent techniques, they're using a lot of cases. They're using some of the sampling techniques. Also, they adopt this kind of geometry concept that developed further the long time ago to design the complete motion planner. Also, this is actually one of our early work that we worked together in with some of my students. This technique is the dancing PRM star, the simultaneous planning of the sampling. Also, this technique based on sampling. Also, the optimization technique, which I didn't talk about yet. I didn't talk about sampling or optimization technique yet, but later I will talk about it later on. But actually here, to do that, we actually utilizing this, we approximately computing this C-space free space, this configuration free space, where we don't have any collision. So instead of the computing ejector, this C free space, we use this approximation technique. I'm not going to talk about all the low-level details. So basically, somehow we approximate C space and utilize further this sampling optimization. That way we can improve the overall performance. Let me show you this video a little bit. Okay, so here actually we generate a lot of samples. Here we generate a lot of samples, so that actually we can see what are the actual obstacle space or free space, and then the samples comes with color. Basically, this color indicates that this one actually this distance to the closest actually the obstacle. So this means that wide empty area. Yeah, at that cases this one is that the red one is the very close to obstacle. This is actually about in the middle. So based on that, we know that what the C obstacle space looks like. Based on that, we do a lot of the motion. We apply that information to accelerate this optimal motion planner. Okay, so if I talked about this C obstacle space and other things based on triangle or polygons, right? But as you can see, in some of the recent, a lot of the current robot actually using a lot of sensors. Like we are using a lot of sensors for computing our current orientation robot. Also, they're using a lot of sensors to observe what are the surrounding objects. So this actually I'm showing the laser-based the sensor. Also, you might heard about the Velodyne sensors here. Then based on this, actually we get the point cloud of the surrounding information. So these kinds of sensors give us usually the point cloud. Point cloud is nothing but a set of points. So here it generates the laser, and then based on this received information, we know at that point actually along what distance we got some certain obstacle, and then based on that actually we got the this kind of the point cloud. Also you see that this kind of Kinect another one. Also the Kinect comes with the RGB sensor, also IR depth sensor. So based on that also it gives us some sort of the point cloud. In other words, in each pixel, in each actually this is image resolution. In each pixel we got also color, RGB color, also the depth. So overall, they actually give us the point, right? And then you can see that a lot of there are actually a lot of the library to handle point. And then basically, if we process those kinds of point cloud, we can even get this triangle and polygon shapes about our robot, also the environment. But right now, a lot of cases actually just using the working directly under the point cloud. But nonetheless, even though actually I explained there are a lot of motion planning technique based on the triangle, virtually all of the digital motion planning technique naturally works on this kind of point cloud. But before we move on to the low level topic about the C space, I'd like to give the kind of the whole picture. So usually we use a lot of sensors, right? This kind of Kinect sensor or some other expensive development sensor, whatever they are. It gives a point cloud about the obstacle map. So basically, we put the sensor, and then we know what are the obstacles around in the surrounding area of our robot. And then we usually perform the SLAM. SLAM is nothing but simultaneously localization and mapping. We look at the surrounding area, and then basically here we look at this portion of the scene. So we look at this portion of scene, and then we match together. So that way we get the bigger map. And then based on that, we also we can compute what is our relative reference location of our robot within that map. So that's actually computing the map. The mapping is nothing but computing map, and localization is that within that map where I am. In other words, where my robot is located. We do that, and then once we know that kind of the map and my location, we can do the actual this passive motion planning. We run the A-star algorithm, or we run some other technique. We compute the path, right? And then we give that path to the control unit. Control is nothing but computer some of the force control that actually derived this motor that built into our robot, right? And then basically the control unit nothing but computer force that tries to follow the computer path from the motion planner. So typically for control unit, there could be a lot of techniques, but one of simple control technique is this PID technique. So we wanted to measure we compute the force that following following particular point in the path, whether this also while satisfying some other property. So if you're interested, I recommend you to look into PID controller, but I'm not going to talk about the low-level details actually. But to design this kind of robot, you need to have the hardware with sensor. Also, there are these kinds of actually modules. Then we can do some operations. Also, built on top of that, if we wanted to do particular operations, let's say I wanted to grab this one, then we need to also have the domain, the problem specific actual technique, motion plan, or the understanding of this object. So basically, it requires a lot of the related actual intelligence or the underlying techniques. Okay, so now I'd like to briefly touch on the path and metrics. So before I already talked about what's the path in the C space. Also, I talked about this trajectory, which is actually parameterized by the time, so that we can control the actual even velocity. But I'd like to talk about this concept of these homotopic passes. So suppose that there are two paths. These two paths, and here actually let's say this is one path, another path, and then sometimes actually the two paths with actually having the same endpoint. In this case, this path and that path has the two endpoint, right? And then if we can deform this one path into another path, then without having any collision, we say that those two paths actually homotopy each other. So these are actually the mathematical derivation. Somehow we find the mapping from the one at the cases. When I have the actual 0 here, it turns out that it's a one path here, and then we actually gradually changing this 0 to 1. Then we actually when it's at the 1, then this mapping turns out to be this path, another path. So basically, in other words, if we can deform the one path to another one, they are homotopic each other. But as you can see in this example, we cannot deform this path into there because of this obstacle, right? So in this case, this path is not homotopic. But actually, why I'm talking about homotopic. So basically, there are a lot of cases that we wanted to find this optimal path, right? So along this line, suppose we actually compute this path, right? Also, we can keep searching around this path, and then we can find the even better path, right? But it's very important to have a capability to try out other paths that actually have a different that are actually not homotopic to the existing one. Why? So basically, since we cannot deform the path in a different homotopic class, it means that we cannot deform this path into that one. It means that we actually find a very different topology of the C-optical space or the C-free space, and there are potential that we can actually have the better paths over there. So basically, it's very important to try out different homotopic classes. So basically, homotopic classes or paths actually contain all paths that are actually homotopic to each other. In other words, the passes that can be deformed to each other, right? So it's very important to explore different homotopic classes to find actually optimal paths, or even actually finding better paths. That's why actually I talk about the concept of homotopic. Also, sometimes when you read the paper about optimal planner, you can see that this concept. Now I'd like to actually talk about metrics. Some of you already know what's the meaning of metric or distance function, right, in the C space. So basically, this is our distance function, and then this function gives us some value, right? This is the non-negative value. And then any metric actually should maintain this one, right? Basically, when this Q and Q prime turn out to be the same configuration, this one should be give us a 0, right? Identity property. And then if we swap this Q and Q prime here, then there should be give us same distance, right? The symmetric property, and also you might see that this actually this triangle inequality. So basically when you have the 3 dot, 1 dot, another dot here, basically the path from here to there, then also we can consider another path from here to there, right? And then the path from here to there should be bigger or equal to this path. That's actually triangle inequality. So any function actually satisfying these 3 properties, we call it the actual metric. Here, one of very common metrics, LP matrix or LP norm. So basically, given 2 configuration, we actually measure the difference between in each element. There could be high dimension space, right? So we measure the difference between in each dimension, and then we take the power of p, and then we sum all of them with in each element dimension, and then we do take the power of one of the p. So one of very common is L2 norm, the Euclidean metric that we know, Euclidean metric that we commonly use. Euclidean distance, also L1 norm is Manhattan distance. L infinity actually L infinity here. If we set the p become infinity, then it gives only the maximum value of the difference of in each across the different dimension. Actually, this is a very common one. But in the case of robots, we can use that one. But this is another example. Let's say we have robot A, and we use x on a particular point on the robot A, and x of q is give us the position of x in the workspace when the robot A actually position at the configuration q. This configuration, and then what's the location there, and then we define the actual distance between 2 configurations. This example, we have in this case triangle robot at this configuration on the robot here, and then we can define the distance between we fetch any point over the robot, and then we actually measure the distance of that particular point at that configuration. In other words, here we actually measuring the distance from there, and then we take the maximum one. Also, we can actually use this as actually metric at that kind of robotic applications. Actually, depending on the metric space, later on we will later on we will use this concept a lot. The metrics basically we need to compute what's distance between 2 points for computing the path, right? So depending on the metric that you are using, actually performance of our motion planner varies a lot. Typically, we use a lot of this Euclidean metric but depending on your domain, depending on your specific problem, basically you need to carefully choose this matrix. But if you don't have clear idea, you can start with using the Euclidean metric. Another one is that suppose that actually we had this we had actually this xy actually xy space for the position, also this the orientation, this q and q prime this configuration. And also we can define their distance like this. Looks like this Euclidean distance. Here, basically the same component of the Euclidean distance, measuring the distance along the x and y dimension. Here also we're just adding the alpha square. Alpha square is nothing but basically what's actually we also measure here. We measure this angle here. Also we measure the other angle, and then we take this minimum angle. So in other words, the minimum angle difference between these two configurations. And then we compute with alpha, and then just we adding the alpha square here. This is one example, right? So in other words, we actually combining this heading or difference, also this distance difference into this equation, right? But you can think that there could be many issues. So also there are some of the papers about what might be the good metric that combine this heading difference, also this position difference. But anyway, I'd like to point out that there could be the many different metrics, and then depending on the metrics, you can actually depending on the metrics, some of the property, also the performance of motion planning techniques varies. If you don't have clear idea, I recommend you to use just Euclidean distance. Okay, so if I talked about the different issues of the C space, I start with the definition, also this constraint. Today I talked about how we can compute the C optical space. Also I talked about homotopy classes, also the kind of the passive related concept. I briefly touch on some of the metric concept here. And then, so if I talked about some of the basic component of motion planner. So under the category of motion planning, I talked about the basic framework, C-space formulation. I talked about discretization as an example. This the visibility graph. I talked about actually also this graph search, A-star algorithm. Then I move on to the classical technique, roadmap as an example. This visibility graph. I talked about the cell decomposition, potential field. And then I actually lay down some of the foundations of the C space. I talked about the minimum dimension of C space, DOF, S of n of also the SE. Also, I talked about the Minkowski sum for computing C optical space, and then I briefly touched on some other geometric topology concepts like the homotopy concept. Also, now that's kind of quick summary about what we have talked about so far, and then later on I will talk about some of the actually another main ingredient for enabling the motion planning, is collision detection and distance computation. The same homework, summary of 2 papers from top tier conference. Go over the next lecture slide, and then you need to come up with the 2 questions before the midterm exam. That's it. Thanks so much. Bye.